All right, let's move on to example 7. So it says solve the equation x squared equals x minus 1. I'm going to go ahead and subtract x and add 1 to both sides. So then we get x squared minus x plus 1 is equal to 0. Now let's go ahead and try to factor this. Since our a value is equal to 1, we would just need to use the x method, and these are the values that go there. I'm picking up the speed a little bit since hopefully you've picked up on what values to put where. So I want to try to find two numbers that add to -1 and multiply to +1. And it turns out that there are no numbers that do that. So I'm going to put these like red dots there to indicate that, there's nothing that we can do for that. So I'm going to go ahead and erase that. And now we're going to use the quadratic formula. So we have -b plus or minus the square root of b squared minus 4 times our a value is 1 and our c value is also 1. And then all over 2a, so 2 times our a value. Now let's go ahead and simplify that. So -1 times -1 is +1. -1 squared is 1. And then if I simplify that multiplication, -4 times 1 times 1 is just -4. I keep making my square root symbols too long. Okay, and then our denominator is 2. Now if I simplify that, I get 1 plus or minus the square root of 1 minus 4 is -3 all over 2. Now, this is a scenario where I told you that the quadratic formula always works unless there are no real solutions. This is an example of that case that I was talking about. We can't take the square root of a negative number and get a real number. We can get something called a complex number or an imaginary number. However, that's not in the scope of this class. So that's something that you might explore in another class. And so for the purposes of our class, if you are simplifying the quadratic formula and you get a negative value under your square root, what that says is that there are no real solutions. And that is sufficient for our class to indicate that there are no real solutions. Okay, and I'm going to talk a little bit more about what that means later on, but for now, let's talk about parabolas. You've probably heard this word before, but if you haven't, a parabola is just the distinct graph of a quadratic function. And if you've seen it before, it kind of basically has like a U shape. And the vertex of a parabola is either the highest or the lowest point on the parabola based on which way the graph is oriented. Now, I'll quickly sketch for you. Here's the xy plane. Sometimes a parabola might look something like that. So it's oriented upwards, and the vertex would be this point right here, and it would be the lowest point. Now, in other scenarios, here's my xy plane, I might have a parabola that is oriented downwards, and so this point right here would be the vertex, and it would be the highest point. So that's the vertex there, and then this one is the vertex here. So it just depends on which way it's oriented. Okay, so example 8 wants us to graph y equals x squared. It might be helpful if we make an input-output table. So I'm going to plug in -3, -2, -1, 0, 1, 2, and 3. Now I'm going to go kind of fast, but notice that the graph of this function or the outputs of this function have kind of like a mirrored quality. And that's because if you take a number and you square it, and you take the negative of that number and square it, it should give you the same outcome. So negative 3 squared is 9, negative 2 squared is 4. So notice that mirrored quality. Okay, so now on my graph here, I'm going to draw in my axes. Now notice in this scenario for this specific function, none of our output values are negative because we're squaring these values. And so if I plugged in negative 3, then my output would be positive 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be right there. And again, it's mirrored. So when I plug in positive 3, my output's also going to be 9. When I plug in negative 2, my output is going to be 4. When I plug in negative 1 and positive 1, the output is both 1. And then if I plug in 0, the output is 0. So I'm going to go ahead and connect my dots. And it looks something like that. And then I'm also just going to put little arrows here to indicate that they go forever in both directions. Now, this is kind of a little bit of a review from a previous section, but maybe we can talk about the domain really quickly. The domain is going to be everything. Notice that our x values continue to go that way and our x values continue to go that way in both directions. So our domain is going to be negative infinity to positive infinity. And then our range, maybe I'll do that in a different color. Our range is the possible y values. Now, notice that our graph does not fall below the x-axis. Because we're squaring our input values, that means that everything's either going to be 0 or positive. So then our range would be 0 to positive infinity. Okay? Another question, what is the vertex of this parabola? Well, because it's oriented upwards and it's like a smiley face, we know that it's going to have a lowest point, which is this point right here, our origin. So in this scenario, our vertex is the point 0, 0. Okay? And so those were just some characteristics of this specific graph. Let's talk about specific characteristics of a parabola in general. So a parabola will open upwards if a is greater than 0, or that's another way of saying positive. And it will open downwards if our a value is negative or a is less than 0. So notice I'm going to rewrite this down here. So we have y equals x squared. Our general form is y equals ax squared plus bx plus c. So notice in this scenario, b and c are both 0, and our a value is equal to 1. Since a equals 1, and 1 is a positive number, that means we're going to have what I like to call a smiley face, because it's opening upwards. If a were a negative number, then our parabola would open downwards, and it would be a frowny face. And we'll see more examples of that later in these videos. Another thing that turns out to be really important is the ordered pair that represents the vertex of a parabola is given by this ordered pair. So we're going to probably use this a good amount in these few sections. So the input coordinate is negative b over 2a, and then the output coordinate for the vertex is just going to be whatever you get when you evaluate the function at negative b over 2a. So again, this is the ordered pair for whatever the vertex is. And we'll use that in example 9.